Swayam Prabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustions, Module 4 Properties of Gas Mixtures. In this module, there are 4 lecture topics. In the last lecture, we covered ideal gas and real gas. Today, we are going to discuss about the next topic, that is gas mixtures and multi-component system. And in this lecture number 16, that is gas mixture and multi-component systems, we will study the following topics. First one is the basic relations for gas mixtures. Then we will move on to multi-component systems, where we will define important properties like partial molar properties, chemical potential, fugacity and ideal solutions. In fact, all these 4 parameters are very vital when you are dealing with the multi-component systems. And this multi-component systems is a generic name. It could be a gas mixture, it could be a gas plus liquid mixture, and at the same time there may be many gases and also there may be many liquids. So basically it means it is the state of a substance either in gas phase or liquid phase and at different thermodynamic conditions in terms of pressure, temperatures. Also they may have different compositions. So the topic is very exhaustive and very complicated. When you are dealing with multi-component systems, we will try to simplify certain analysis where a generic or overall picture can be projected, and we will deal with the substances which are in mainly gas phase, and mostly we will be concentrating this is an ideal gas mixture in a multi-component systems. Of course, towards the end of our lectures or modules or this course, we will be dealing with the combustion systems where the combustion products also comes into pictures. That is we have reactants, and after these reactants, when they get oxidized, then we get the combustion products. And in fact, this combustion product, for these combustion products, we know that after combustion the reactant vanishes, but what we have left out is the combustion products. So such a systems also has a great resemblance for the analysis of multi-component systems. So there are wide variety of examples, and we will be dealing with very simple thermodynamic aspects of a multi-component systems. First thing what you need to do, how to deal with the thermodynamic properties. So prior to this lecture, we have PBT data for pure substances. We have told that these data are available in the tabular form or the property tables, and they should be used as and when it is required. And looking at these data, when you deal with the multi-component systems, another parameter that pops in is the compositions. These compositions are mainly analyzed either on mass basis or molar basis. But when you deal with the multi-component systems, it is ideal to use a molar concept, because the molar concept is uniform. While dealing with the molar systems, we can deal with one gas constant, that is what we call as universal gas constants when dealing with the equation of states. So that is the advantage when you deal with the multi-component systems. it is better to use the molar properties. So, for that these 4 parameters are of importance, like partial molar properties, chemical potential, fugacity and ideal solutions. And in fact, this ideal solution is another model of gas mixtures. Normally when we have liquid and gas together, then we say it is a solutions. But in some extent there are some relations which are suitable for ideal solutions. If you can use them for analysis of gas mixtures, it also gives a good estimates. So that is the reason that this gas mixture and ideal solutions has a some definite linking among them. So, we will study one by one of these properties down the lectures. So, let me start with what do you mean by gas mixtures. So, I have given a brief introduction about the gas mixtures. Just to summarize, that many systems of interest that involve gas mixtures, they consist of 2 or more components. There may be unlimited variety of mixtures that can be formed from a given set of pure components by varying their relative amount. The principle of thermodynamics what we have introduced so far is also applicable systems involving mixtures, but these principles also require the evaluation of mixture properties. There we are talking about the individual properties, thermodynamic properties for an individual pure substance, and here we will have to find out the how those concepts can be extended for mixture to evaluate the mixture property. The most techniques for estimating mixture properties are empirical in character, and they are derived from the fundamental principles. For certain generic substances, the mixture properties are also available in tabular, graphical form or equation forms, or we can say state equations. We are now going to deal with the methods for evaluating PVT relations for pure substance, which can also give a realistic estimate for gas mixtures. So, first we will briefly discuss about the property evaluation of gas mixtures, which can be considered as an extension of PVT relations of the pure components. So, in a summary what we can say, each pure component is consist of a gas single phase, that is gas, and when these gases mix they form a mixture, and there also we say that this mixture also assumed to be another pure component. So, this is the main assumptions for the evaluation of mixture properties. And but the first thing that we need to know is the knowledge of compositions. As I mentioned, the ideal way of looking at the mixture is through their mole fractions. So, the mole fraction is defined by in a mixture if there are multiple number of components. For any components, the mole fraction yi is defined by number of moles of that I component divided by total number of moles. And in fact, the summation of this mole fraction in a mixture is always 1, and the summation of total number of moles, that means if there are j number of constituents in a mixture, the total number of moles can be added to find the total number of moles. Now, when you deal with these things to calculate the equation of state, that means previous lectures we have talked about different state equations, that is ideal gas, then we have van der Waals gas equations, we have virial state equations, we have Redlich-Kwong equations, and they gave some kind of estimate of the thermodynamic states. And now here what we are trying to say, if for a mixture analysis those equations also can be recalled. Like here if you see, there is a Redlich-Kwong equation which is talks about P is equal to R bar T divided by V bar minus B minus A by V bar into V bar plus B to the power half. This equation also can be used for mixtures, but what changes we need to do? Evaluation of the constants eval A and B which is appearing in these equations. This evaluation of these parameters A and B has to be component wise, then they have to be summed up. And again, while looking at the equations, we have to also see that how in the equations what form they appear. For example, in this particular equations there is a t to the power half term. So, a proper judgment has to be made that how this summation has to take place. One way of looking at for this particular case, the value of A for the mixtures can be found out from the component analysis through summations, where we can sum of all the components yi a to the power half and then we make it square. So, basically this gives a good estimate which correlates with respect to these equations. So, this type of mathematical jugglery you have to make more realistic estimate. But whereas for B term we do not have to look into, because they are having a linear relations, we can simply write B is equal to summation of yi and bi. So, the idea of looking at for this, that we have to make appropriate judgment while evaluating the constants in a state equations through their summation. The next relation that we are going to apply is case rule. Case rule talks about the evaluation of the properties based on the principle of corresponding states. In our previous lectures, we discussed about the reducing the parameters like pressure, temperature with respect to reduced parameters, and this reduced parameter was done by taking the values at the critical point for that pure substance. That means we require critical pressure and critical temperature for a pure substance. Based on that, we can find its reduced parameters. Through these reduced parameters and through this compressibility chart, all other properties can be estimated. Now, case rule says that we will also try to apply same fundamental principles based on the principle of corresponding states, but here we will look at them as a mixture. For example, if there are multiple number of substances, for each substance we know its mole fractions and we also know its critical temperature and critical pressures, then for the mixture critical temperature and pressure can be found out through this summation. So, Tc is equal to summation of I is equal to 1 to j yi Tci and Pc is equal to summation of I to j yi Pci, and these overall parameters along with the compressibility factor can be used to evaluate the mixture properties. Then moving further, there is another rule which is called an additive rule, and this additive rule applies for pressure and volume of the mixture. That means we say that mixture is at overall pressure P and temperature T. Now, how that overall pressure and temperature needs to be evaluated? So, for that we have these additive rules. These additive rules apply to evaluate the pressure of gas mixtures when they occupy a volume, total volume V and overall temperature T. And when we have this, we can apply this additive pressure rule, that is mixture pressure is equal to individual pressure P1 plus P2 and then plus P3 and so on, and they summation of these things and they occupy a common temperature and total volume V. And of course, through this we also have to find out the compressibility factor for these mixtures by knowing the mole fraction of each component and its individual compressibility factor, and this has to be evaluated at overall temperature T and V of the mixture. From this we also can find out the compressibility factor for individual component. For that we have to recall its individual pressure, that means we call it as partial pressure of that particular component, then we have to use its mole fractions. Likewise, we can evaluate individual pressures and then total pressures. Now, same rule also applies for volume. Now, if you say that total volume is equal to sum of the volumes of each component 1, 2, 3 and so on, and we use the same compressibility equations to find the individual compressibility factor, individual volume and total volume. So, basically additive pressure and volume rules can be formulated in terms of compressibility factor. Now, having said this, we will now move on to multi-component systems. Now, here we will have to, as I said, that a multi-component systems is a very generic topic and there may be very complicated mixtures, their phases, their compositions, their relative individual pressures and temperatures, so all sorts of things. But to simplify these things, we will primarily emphasize analysis of multi-component systems for gas mixtures. That means we can say deal with the gas mixtures and to some solutions. Typically, when the liquids and solids are under consideration in a multi-component systems, we call this solution. We use the word solutions. Otherwise, when you use for gases, it is usually term is used as mixtures. Now, for to deal with this multi-component systems, there are three parameters of importance. One is partial molar properties, chemical potential, and fugacity. So, we will deal with them one by one. So, let us talk about the partial molar properties. What does this mean? That means if you can think of a system consisting of n number of, maybe j number of gases, with each with individual components n1, n2, n3 and maybe nj, and they have a common pressure P and temperature T, that is overall pressure and temperatures. But what we want to know is that each component N1, N2 or each component of these things, they are treated as a pure component. Now, when they are treated as a pure component, they have their individual properties like internal energy, enthalpy, molar volume, all these things. So, when they are treated as a pure component, they are considered as with respect to their molar numbers. Now, when this mixture is considered with respect to its overall volume V, okay, then what we have is that this mixture has a relative role. That means this mixture with respect to total volume will have a different number. So, for means that while dealing with these molar properties, we deal with the properties which needs to be evaluated with respect to its individual parameters of the component, and also when you deal with, but when their properties are defined with respect to overall conditions of the mixture, pressure, temperature or volume, then they are treated as a partial molar properties. So, let me put this definition as that the term partial molar property is the property of the mixture. It is a property of mixtures that we should know, but it is not the simply of property of a specific component. And then the extensive properties of the mixture can be expressed as weighted sum of the partial molar properties. So, in a general case, let us consider an extensive properties X. These extensive properties can be applied for usable for volume, internal energy and enthalpy and entropy. So, for a single phase single component systems, we write X is equal to X as a function of temperature, pressure and its composition, number of moles. Now, same thing when you represent it for a multi-component systems. So, this one that there may be number of components N1, N2, N3 and each will have number of moles N1, N2, N3 and Nj. So, we write for these things. Then what we do is that then you have to define the partial molar properties for the component. So, same expression, that means if I write this particular X for this individual constituents components I, Xi I can write it as Xi, if this Xi is defined with respect to the overall multi-component systems with same as X is this, then corresponding Xi would be dou Xi by dou Ni into Tp into Ni. So, this Xi bar is equal to dou X by dou Ni, Ni is the number of moles for that component I, and this differentiation has to take place at mixture temperature, pressure and but with respect to component Ni. Then this is called as partial molar properties. Now, this rule can be applied for the volume V, then we can also write for the internal energy U, we can write it for enthalpy, we can also write it for entropy. So, this is how we define this, and in terms of moles we can write with respect to the Ni stands for number of moles, Bi stands for molar volume for the component I. So, here is the total volume of the component is equal to summation of each individual molar volume multiply its mole fractions. So, this is how the partial properties are defined for a component in a mixture, and this rule also is applicable for all properties like enthalpy, Gibbs function, Helmholtz functions and so on. Now, one way to calculate this, there are of course the molar properties are can be found out for individual components. There are many techniques that are available, that several methods we can do it analytically, numerically and in the form of tabular forms of data. But if suitable data are available, one simplest way of representing is in the graphical form, which is called as method of intercept for any extensive property x. So, what do you do is that you take this simple coordinate systems x, y, that means two y axis or two ordinate axis, one abscissa axis, and abscissa we put is as a mole fraction, and ordinates, one way we can find out one ordinate we put it for molar volume for component A, and other side of this ordinate we have molar volume for component B, and each mole fractions we can locate these points and draw a curve. So, the curve that stands for is that if I take any particular line on this axis, left side of this ordinate, and we will arrive it is a pure component, and in this line there is no component of phi, and on the right side of this line, that is this thing, we have pure component B. So, basically this point stands for molar volume Va at Tp for the component A, and this point stands for molar volume, specific volume for B at T and P. And so, basically if you want to find out any value on this point, so we can draw a tangent, and wherever they intersect we can find out the molar volume, that means total molar volume for the component A, T, P and Yb. So, this way we can frame the method of intercept equations for a two component systems as total volume V will be the number of moles for the component A into V bar A, that means molar volume for the component A, and Nb into molar volume for the component B. So, by simplifying these equations, and that means when you divide by number of moles, then we write V by N, that is molar volume for the mixture, is 1 minus Yb into Va plus Yb into Va Vb, or you can write Vb molar volume for A plus Yb into Vb minus Ba. So, this is the simplest way what we can find out for the molar volume in a partial molar properties in a mixture. Then in many instances we also require the change of the volume during the mixing. So, that means the component I will have individual molar value, specific volume, molar specific internal energy, molar specific enthalpy, but after mixing it will have a different number. So, then that means there is a change in the volume of the property after mixing. So, that mixing properties we can find out delta V mixing is V mixer minus V component. So, had these properties be treated as a total volume, then it would have the mixer volume has to take the form summation of Ni into Vi bar. If they are treated as a component wise, then it will have its own Ni into its own specific volume when it treated as a pure components. So, difference will give you the volume change for during mixing. So, similar expression can also be found out for internal energy, enthalpy and entropy after mixing. So, this is how the partial molar properties are defined. Now, we will move on to another important properties for mixture, and that is called as a chemical potential. So, among all partial molar properties, the partial molar Gibbs function is useful in describing the behavior of mixture and solutions. This partial molar Gibbs function for an arbitrary component I is termed as the chemical potential for the same component, and this chemical potential is an intensive properties, and it plays a very central role for chemical and phase equilibrium for a multi-component systems. So, what does this mean is that, so we all know that we have the term enthalpy, we have term the Gibbs function, we have Humboldt functions, but what the chemical potential means, it is the Gibbs functions that take the lead role. So, for an chemical potential, component I in a mixture is defined as mu I is equal to molar value of Gibbs function for the component Y, that is equal to dou G by dou Ni at T, P and Ni. Otherwise, we write G as, where G is summation of Ni into mu I. So, from this equation we can find out that G will be, Gibbs function is nothing but Ni into mu I when it takes a summation from I is equal to 1 to j. Now, based on these chemical properties, we are now going to alter the enthalpy, Gibbs function and Humboldt functions in this form, where the term chemical potential is introduced, that is mu I is introduced in all the equations. So, based on that, we have another important equations for the mixture, which is called as Gibbs-Duhem equations. Like we have earlier time, you have used Maxwell equations, and while dealing with the mixtures, we arrive at another equations what we call as Gibbs-Duhem equations, which is equal to V dP minus S dt is equal to summation I to j Ni into d mu I. Now, let us find what is the role of these chemical properties when dealing with the analysis of the mixture. The next important property which is has a similar viewpoint with respect to chemical potential is the fugacity. Now, we may ask what is the role of fugacity, and we also say that fugacity has a similar role with respect to chemical potential. Now, let us say what is the demerits, or why another term we are using fugacity in place of chemical potential. It has been shown that fugacity is a well behaved mathematical function. In fact, chemical potential mu I is also a mathematical function and fugacity is also a mathematical function, but it is a well behaved. Well behaved means that it gives a realistic approach, something like that. Now, how that happens? So, let us analyze the consequence of a chemical potential, and if we represent it in terms of fugacity, what advantage we will get. Now, for a single component systems, when you talk about Gibbs function, that is nothing but n times mu, so that we find mu is equal to small g bar, that is g by n. Now, in one of the thermodynamic relations, we recall in our previous module, specific volume is equal to dou G by dou P at constant T. Now, by putting this in terms of chemical potential, we can write this equation as dou mu by dou P at constant T. Now, if we apply this concept for an ideal gas, that means you define a chemical potential for an ideal gas. So, for an ideal gas, we can write the molar specific volume is equal to R bar T by P, and for that we write, instead of mu we write mu star. So, this particular equations can take the form as this, that is dou mu star by dou P at constant T is equal to R bar T by P. Then after integrating this, you arrive at these equations like mu star is equal to R bar T ln P plus C of T. But here the important consequence that we see, that when P tends to 0, when P tends to 0, mu star is not defined. So, it poses a mathematical problem how to deal with this fact, that when you find out the chemical potential for a mixture for which the pressure tends to 0, what is going to happen? We do not have any answer. For that, we define another function what we call a fugacity, that is what we call this as a well behaved mathematical functions. So, how it behaves well? So, instead of writing mu star, we define this f, we define this mu, the fugacity, in terms of fugacity we define this chemical potential mu, and instead of writing P here, that is replaced with a parameter f. So, chemical potential is expressed in terms of fugacity, mu is equal to R bar T ln f plus C of T, so that from this equation we get V bar is equal to dou mu by dou P at constant T, that is R bar T. Instead of these things we have ln P d of ln p by dp at constant T. And what we see is that at the limit of 0 pressure, this V bar, which is R bar T ln f by dp, that point at the limit of 0 square, limit p tends to 0, f by p is equal to 1. Okay, f by p is equal to 1. So, this condition, that means at 0 pressure, a different treatment was, when pressure tends to 0, mathematically it is treated in a different form in a limiting situations, where limit p tends to 0, f by p is equal to 1. Other way is, I can say that fugacity plays the same role as that of pressures, but if improves the mathematical functionality at the limiting conditions. So, based on this, so once you know the fugacity, instead of chemical potential, if you represent in terms of fugacity, it has some other advantages. This fugacity also can be found out with correlations from the compressibility factor at reduced pressure PR, reduced temperature TR for the mixture, and based on these reduced conditions, we can also find out the generalized equation of state that gives Z, that means compressibility factor, as a function of PR and TR. How you are going to get it? So, let us start with the expression for fugacity F, and that we start with the basic definition, mu is equal to R bar T ln f Ct. Okay. So, at the limiting case, when you say limit p tends to the 0, f by p is equal to 1, then we recall this expression Z is equal to p v bar by R bar T, or we can find out the v bar. You now replace this v bar in terms of Z. So, we write this R bar T d of ln f by dp at constant T will be R bar T Z by p. From the both sides, these two gets cancelled. So, ultimately we land off d of ln f by dp is equal to Z by p, and Z is your compressibility factor and p is your pressure. Now, when you subtract minus 1 by p from the both sides, then it will give you a integrations in a workable form, what we call as ln f by p is equal to integration 0 to p z minus 1 d of ln p. This particular parameter, and instead of p we can use it in terms of PR, that is reduced pressure. So, this will tell us that how you are going to evaluate the fugacity. Now, let us see how you are going to get. Is that if you go through any thermodynamic books, you will find one particular chart which talks about fugacity coefficient. So, basically f by p is nothing but your fugacity coefficients, although that means f approaches p, but f is not equal to p. So, that is the reason we call this as f by p as a fugacity coefficient, and this fugacity coefficient in a mixture is represented in terms of the reduced parameters. So, PR stands for P by PC and TR stands for T by TC. So, we have TR is equal to T by TC and PR stands for is equal to P by PC. PC and TC are the critical pressure and temperature for that substance. Either you can get it for an individual component pure substance, but here the fugacity coefficient, when we are talking about, we are talking about the mixture. So, basically we have to find out the mixtures critical pressure and temperatures, and from there we have to find out the fugacity coefficients. So, when we are represented, so you can see this is the temperature line. At different TR we will have different reduced pressure values. So, basically for a given data you have to find TR and PR. So, let us say you have PR 4 and TR may be 0.85, this point, no, look at this point gives you this number, fugacity coefficient f by p is equal to close to 0.1. So, this is how this chart has to be referred. Now, we will talking about the fugacity coefficients for a multi-component systems. When you deal with the multi-component systems, basically we have to find the fugacity coefficient for this individual component I, also the fugacity of the overall mixture. So, based on that we have two numbers like if the component I is treated in the mixture as a mixture, that is mu I, and this same component I is treated as pure components, it will have a molar specific volume Vi, and you will have, when it is mixture, it will be a mixture volume Vi bar. So, difference between these two, that means if you can subtract between these two, Vi and minus B bar will be represented in terms of the fugacity. So, capital Vi bar minus small vi bar is equal to R bar T rho of ln Fi bar by Fi into dP. And after performing the integrations, we will arrive at the workable form, that means which relates the mixture fugacity and fugacity for the component I, means we say the fugacity for the component I in the mixture and the fugacity for the component I if you treat it as a pure component. But all these things are taken at the given composition and temperature and pressure. Okay. So, the last part of our lecture today is the ideal solutions. So, many a times till this point of time we have talked about the different parameters that are useful or they need to be calculated for evaluation of the thermodynamic parameters of the mixture. But what we are going to discuss now is an ideal solutions, and the advantage of the ideal solution is that it gives a simplified version. What this ideal solution is, that it follows a rule what we call as Lewis-Randall rule. That means an ideal solution follows a rule what we call as Lewis-Randall rule, which says that the fugacity for the component I in an ideal solution is equal to yi times Fi. That means fugacity of the component I as a pure component when it is multiplied by its mole fraction. So, this particular relation is applicable for ideal solutions, but in our previous slide we said that we find the difference in the volume Vi bar, capital Vi bar minus small vi bar, that is expressed in terms of fugacity. Now, when you apply this Lewis-Randall rule for that equation, what is going to happen? So, this we see here is that, and or what will say, what is the advantage of assuming mixture to be treated as ideal solution is that when you use this concept of ideal solution or Lewis-Randall rule by taking Fi bar is equal to yi times Fi, then we recall these particular expressions Vi bar, capital Vi bar minus small vi bar, which is R bar by T into d of ln Fi divided by dFi into dP. So, this particular term vanishes because this we have used this Lewis-Randall rule. When you vanishes, it gives a simple type of expressions, that is Vi bar, capital Vi bar is equal to small vi bar. It assumes that volume of an ideal solution V is nothing but the summation of the total volume Vi of each component. This is nothing but your additive volume rule, and similar way, that means the ideal solution follows this additive volume rule. So, this gives the simplified version of our calculations while dealing with the fugacity if they are modeled as an ideal solutions. So, of course, through this modeling what we can find out is that partial molar internal energy enthalpy of each component of an ideal solution can be calculated, and it is seen that if you use this concept of ideal solution, the partial molar properties of internal energy enthalpy of each component of an ideal solution is equal to molar internal energy and enthalpy of the corresponding pure component at the same temperature and pressure. But this rule does not apply for entropy, because entropy increase during a mixing, entropy of the things always increases. So, basically we can apply this for internal energy and enthalpy, but we cannot apply for entropy because entropy is associated with an irreversible phenomena, and separation of mixture into pure component would never occur simultaneously. Okay. So, this is how what we have dealt so far, that ideal solution modeling will help us in simplifying the analysis of gas mixtures. So, now we will try to solve some simple numerical problems, and here there is no numerical problems, rather it is a derivations. So, basically in one of our slides we introduced Gibbs Duhem equations, which is V dP minus S dt is equal to summation of y is equal to 1 Ni into multiplied by du mu y, where mu y is your chemical potential and Ni stands for number of moles for component I. So, how to solve these equations? To solve these equations or to prove these equations, what we have to recall? These three important things. First one is Gibbs functions. Gibbs functions we say is a function with respect to, we say Gibbs function. So, by definition we write it as temperature, pressure and compositions of different gases N1, N2 and Nj. So, based on this we can find its partial differential dg is equal to dou g by dou t at constant p into n into dt plus dou g by dou p at constant t and n into dp, plus for this entire things we can write in terms of summation I is equal to 1 to j dou g by dou ni at constant t, p, ni and dni. So, we can recall the property relations. Few property relations are like we have B is equal to dou g by dou p at constant t and n. This we derived in the previous module. Minus S is equal to dou g by dou t at constant p and n, and of course mu I chemical potential is dou g by dou ni t p ni. So, these three things when you introduce here, so this expression takes the form dg is equal to dg by dt at constant p and n, it is minus s dt, plus dg by dp at constant t, it is v dp, plus this particular term we can write it as summation of mu I d ni. Okay. So, from this equation we arrive at this. Then by definition of Gibbs function, we can write g is equal to summation of ni into gi bar, I is equal to 1 to n. This di gg bar is nothing but n to j. We can write dgi by dni, and this is nothing but summation of I is equal to 1 to j mu I dni. Okay. Then by substituting this here we write, so we have this equation and we will have another equation by differentiating dg. We will have summation of y is equal to 1 to j ni d mu I plus, sorry, it is mu I, summation of I is equal to 1 to j mu I d ni. So we have equation 1 and equation 2. When equating, we can prove that v dp minus s dt is equal to summation of ni d mu I is equal to 1 to j, because these two terms will get cancelled. Okay, so this is the derivation that we get, gives Duhem equations based on the concept of thermodynamic property relations. This next problem we are going to introduce to calculate the change in the chemical potential. So change in the chemical potential, by chemical potential we have is represented in terms of mu. So change in the potential means we are going to find out change from state 2 minus state 1. We need to calculate what is mu 2 by mu 1. So by definition we write mu is equal to r bar T ln f, that is in terms of fugacity as a function of T. So this mu 2 minus mu 1 will be r bar T ln f2 by f1. Okay, and this we can write it as r bar by T ln f2 by p2 into p2 by p1 into p1 by f1. 1 and 2 stands for states. So we have state 1. State 1 we have water at 400 degree centigrade. So state 1 is 200 bar and 400 degree centigrade. State 2 240 bar and 400 degree centigrade. And for water the critical values are PR, critical pressure is 220.9 bar, critical temperature is 647.3. This data you can find out from the tables in any thermodynamics books. Okay, but what we require is reduced parameters, and here if you can see that we have reduced the fugacity coefficient f by p is represented in terms of PR and TR, sorry, PC. So we have to find out what is PR or PR state at state 1, PR1, that is P1 by PC. This number is 200 by 220.9. This is 0.91. TR1, T1 by TC. T1 is 400 plus 273 divided by 647.3, that is 1.04. So PR and TR will give you F1. So for this PR and TR, from this coefficient will give you F1 as F1 by P1 close to a value of 0.755, somewhere here. And similarly TR2 is equal to T2 by TC, 1.04, it remains same because temperature remains same. PR2 P2 by PC, this value is 1.09. So this will give you the fugacity coefficient F2 by P2 is equal to 0.7. So you have all the numbers F2 by P2, P2 and P2 and P1 data are given. So you can find out by inserting this value mu2 by mu1 is equal to R bar T ln 0.7 into 240 by 220 into 1 by 0.755, and you all know what is R bar. It is 8314 joule per mole Kelvin, and temperature is 400 degree centigrade, 673 Kelvin. So this number will give you mu2 minus mu1 is equal to 597 kilojoule per kilomole. So chemical potential for potential change between these two states is 597 kilojoule per kilomole. So with this I conclude this lecture for today. Thank you for your attention.